Scott's Geography Notebook. Did you want to try saying it?
Da, da, da.
We're going to talk about rising air, and there's a few things that I want to talk about. First, I want to talk about why does this make air cold? Cooler. Next thing I want to talk about is how do we get it to rise? And then I want to talk about the change in temperature. So the first thing we're going to do is, why does this make our air parcel colder? So I have a fake air parcel. Here's my air parcel, and inside the air parcel I've got my little molecules, and my molecules are there, and they're moving around or they're bouncing all around. Now this is the kinetic energy of those molecules that we can see. And they're bouncing and they're banging into each other, and they're keeping pretty active because they're so close together that they don't have a lot of room to bump around. Now, we know that when you go up a hill, that the air might be pretty dense down below, but as you go higher, the air gets thinner. Okay. How do we know this? Well, the scientists have told us so, and we can measure the air pressure down here and down here. And when I take my bag of potato chips up the mountains, because I like going to the mountains and I like taking chips with me, it starts to get all poofy on the outside. It pushes all away. That's because the air is thinner up here than what we have down here. Okay, same thing's going to be happening as we just go straight up vertically as well, as opposed to just going up that hill. But we'll come back to this hill idea. Good, so as this air parcel that's there is able to go higher, it actually has room to expand. So I'm going to take my air parcel and make it a little bit bigger, and it's going to have the same number of air molecules in there. Okay. Now they're moving around, but they're bumping into each other less often. They're going to be bouncing around each other less frequently, and that's going to be measured in a lower kinetic energy, which is temperature, right? Because temperature is going to be the kinetic energy of those molecules moving. Well, if it continues to go up higher and higher, then this parcel just gets bigger and bigger and bigger, and eventually those molecules have so much space that they're able to move around in there, and so our temperature is getting colder and colder and colder. That's why when an air parcel goes up, it expands, and there's more room for those molecules that are in that air parcel to move around, and so they're banging into each other less often. They're going a little bit slower because of it, and the temperature is going to be getting cooler and cooler and cooler. Now, the inverse can happen if an air parcel is forced to come down, and that air parcel is forced into a smaller area. Then the air mass, the molecules get compressed together, and when those molecules get compressed together, then they start banging into each other more and more frequently, and that's going to be causing our temperature to go back up. So parcel that rises, going up, it has room to expand to something bigger. And on the other side, if, like coming down this side of the mountain, if that air parcel is forced downwards and it's caused to become smaller and smaller, then it's going to be getting warmer. So this is going to be rising and cooling. And this is going to be sinking and heating. Sinking and heating by compression. Okay, it's getting tighter and tighter. Okay, now what if we wanted to get a parcel to go up? There's a few different ways that we can do that. One way is if it's going to be over a hot surface. Hot surface. Like out over the desert, or maybe it's going to be inside a city, and that's going to be heating the overlying air, and that's going to be causing that overlying air to have greater kinetic energy, and moving around more, it needs to expand, and so it goes up. And this is referred to as convectional lifting. Convectional. Okay, now convectional is basically just movement up and down. Advection going from side to side. Convectional lifting. And there's another way. Another way that we certainly see here in California is if you have a hill or a mountain or something like that. And if you have the air and the air is being forced towards that mountain, and as it's forced towards the mountain, it's forced to go up and over that, that's referred to as orographic lifting. Orographic lifting is going to be going up and over a surface. Okay, so we have convectional lifting, we have orographic lifting. There's one other spot that we've talked about a little bit already, but that's going to be if you have very, very cold and dry air, like in our polar regions, and maybe this looks familiar, we have our polar front. And then we have this very warm and moist air that starts coming along. Okay, now this is cold and dry, and therefore it's going to be a little bit dense. Okay, cold, dry air, it's not moving around very much. All those molecules are really close together. Well, this is going to be warm and humid. And because it's warm, it's going to be less dense. And this is what we have going on in our mid-latitudes. This is going to be our polar fronts that we have. Okay, so this warm, moist air, if either one of them start pushing into each other, this air is forced to go up and over, and that is referred to as polar front. Frontal lifting. Convectional lifting, orographic lifting, frontal lifting. There's one last one that we'll see in equatorial area. Okay? And this is going to be where we have very warm air from one location and warm air from a different location, mainly in the intertropic convergence zone. But what we can have is we can have air moving from one spot, air moving from another spot. If we have a low pressure system there on the surface, then that air goes up because it has nowhere else to go. It's crashing into itself, and so that air is forced upwards. Okay? That is where air is converging in on each other, so it is called convergent lifting. All right, so those are our 4 lifting mechanisms. We have convectional lifting. That's just going to be warm surface. It rises. Orographic lifting, it's going up and over. Convergent lifting, that's where we have air coming in from all different directions and it's forced upwards. And frontal lifting, where we have cold, dry air and warm, humid air, and they crash into each other. That warm, humid air is forced upwards. All right. Now, we have talked a little bit over on our last sheet how when air goes up, it's going to be getting cooler because of expansion. And when the air comes down, it's getting warmed by compression. There's a term for that. When we're talking about heating or cooling based on expansion or compression, we call it adiabatic. Cooling or heating. Okay, there's a lot of variables out there in the world, but for this one, we've pretty much narrowed down what the temperature is. As our air mass goes up and cools by expansion, if we were at sea level and 1,000 meters and 2,000 meters, the rate of change is 10 degrees Celsius for every 1,000 meters that air parcel rises. Okay, same thing is going to be true the other way. As this parcel is forced to come down and is compressed, it's going to be heating by positive 10 degrees Celsius per 1,000 meters. This one, of course, would be getting cooler, or negative 10 degrees Celsius for 1,000 meters. So what do we got? We've got rising air. When it rises, it's able to expand. Because it's able to expand, the molecule is bumping less often, and so it gets cooler. We can get it to rise one of 4 different ways: through convectional lifting, orographic lifting, frontal lifting, or convergent lifting. And when that happens, the temperature is going to change at the adiabatic rate. Okay? The adiabatic rate just has to do with expansion or compression. So if we're going up, it gets colder by negative 10 degrees Celsius per 1,000 meters that it goes up. 20 degrees, 10 degrees, 0 degrees. And as it comes back down, it's going to be heating by compression.